Welcome to the Deep Dive, where we take the sources you share with us, the deep research, the dense articles, the complicated spreadsheets, and cut straight through to the knowledge that truly matters.
Today, we are tackling a concept that, depending on your perspective, is either the most powerful creator of generational wealth or, well, the silent accelerating mechanism of suffocating debt.
That's right, we're diving into compound interest.
We are.
Our listeners shared a fascinating stack of sources detailing the mechanics, the mathematics, and the surprisingly long, often controversial history of this concept, a concept you often hear dubbed the eighth wonder of the world.
And our mission today is, I think, pretty ambitious.
I'd say so.
Yeah.
We're going to take these dry mathematical constants, this detailed historical context, and some frankly intimidating formulas, and distill them into absolutely essential, actionable knowledge.
So that by the end of this, you understand not just what compound interest is, but really how it operates.
Exactly. How it operates from, say, ancient Babylonian accounting all the way up to the complex pricing of financial derivatives today.
And we really need to drive home that how it operates part, because compound interest is incredibly powerful because of its simplicity. At its core, it's just interest earned not only on the initial money you put down, the principal,
Right.
but also on all the interest that is already accumulated.
So the interest itself starts earning interest. It's like your money is constantly giving birth to more money, and then those babies also start producing cash.
Precisely. That compounding effect is the source of its massive power. It's what drives that exponential growth in investments over decades.
And it's also what makes the total repayment on, say, a 30-year loan so much larger than the original amount you borrowed.
It's the exact same engine, just running in reverse.
Okay, let's unpack this with the core key distinction right at the very top. When people talk about interest, they often mix up two fundamental concepts: simple interest and compound interest. What separates these two financially?
The defining difference is what base the interest is calculated on in the next period. With simple interest, the interest you earned in previous periods is never added back to the principal for the next calculation.
So you're always earning interest based only on that original amount you started with.
Always. It never changes.
Let's run a quick example.
Yeah.
Say I deposit $1,000 in an account that pays 10% simple annual interest. After year one, I have $1,100.
Right.
After year two, the interest is calculated again on the original $1,000, so I earn another $100, bringing me to $1,200.
That's spot on. The calculation always starts fresh from that initial $1,000 base. Now, with common interest, that previously accumulated interest is retained or reinvested and added to the principal.
So it forms a bigger base for the next calculation.
A bigger base, exactly.
Okay, using the same example. $1,000 at 10% compound interest. Year one, still $1,100.
Same result.
But in year two, the 10% is calculated on $1,100, not the original $1,000. So I earn $110 in the second year, bringing my total to $1,210.
And while that extra $10 seems, negligible over 2 years.
It's nothing.
Right. But imagine extending that period to 40 years. That small difference over a single year becomes seismic over the long haul.
That's the fundamental difference that dictates whether your portfolio is coasting or rocketing.
That's the one.
Speaking of rocketing, let's move into the vocabulary that defines the speed of that rocket. The source material highlights one variable above all else that dictates the velocity of compounding.
And that's the compounding frequency.
The compounding frequency.
This is where the simple definition meets the practical mechanics of finance. We use the variable n to define it. It is simply the number of times per unit of time, which is almost always a year, that the interest you earned is officially capitalized.
Capitalized meaning added back to the principal.
Added back to the principal balance, yes.
So if a bank advertises that they compound interest yearly, our n is 1. If it's half yearly, n is 2.
Yeah.
But wait, if I have two products, both offering a 5% annual rate, but one compounds yearly and the other compounds quarterly, so n equals 4, why does the quarterly option yield more money?
That's the critical insight. The more often n increases, the more chances the accrued interest has to start earning interest on itself within that single year.
Oh.
Even though the annual rate is the same, the quarterly compounding means your money starts growing on a slightly bigger base 3 extra times before the year is out.
I see. It's about leveraging that exponential power sooner and more often.
Exactly. And we see concrete examples of this across all financial products. We have Yearly, half-yearly, quarterly, and then monthly, where N is 12, which is probably the most common for consumer debt and savings accounts.
Right, like credit cards.
Credit cards, mortgages, savings. But it doesn't stop there. Interest can be compounded weekly, so N is 52, or daily, where N is 365. And then ultimately we reach the mathematical limit of continuous compounding, where N goes to infinity. We'll get to that later.
Let's focus on that common monthly example, because that's what most people interact with.
Mhm.
If I have a 12% annual nominal rate, but the interest is capitalized monthly, the frequency is 12. But the period for calculation changes, doesn't it?
It does. You're dividing that nominal annual rate, the R, by the frequency, which is 12. So 12% divided by 12 is a 1% monthly rate.
Okay.
You then apply that 1% rate 12 times over the year, but each time on a slightly larger principal. This is what generates the slightly higher effective return compared to that stated 12% nominal rate.
This brings us directly to a key actionable takeaway for our listener. If every product uses a different compounding frequency, one compounds daily, one quarterly, one semi-annually, how is a consumer supposed to compare them fairly? How do you figure out which one is genuinely the better deal?
That confusion is exactly the problem that the annual equivalent rate, or AER, solves.
AER.
Right. This standardized metric is also known as the effective annual percentage rate, or EAPR, or sometimes annual percentage yield, APY. Its purpose is pure standardization.
So it cuts through the noise.
It strips away the compounding frequency, the daily versus the quarterly, to give you a single comparable figure that represents the true cost or true yield of the money.
So if I'm looking at two different savings accounts, and one offers a 5% nominal rate compounded daily, and the other offers 5.1% compounded semi-annually, the only number that really tells me which one is better is the AER. Is that right?
That is the single most critical, actionable piece of knowledge here. If you only remember one thing about comparing financial products, it's the AER. Ignore the nominal rate. That's just marketing.
The headline number.
It's the headline. Pay attention to the AER because that tells you the real yield after the effects of compounding have been factored in for one full year.
I appreciate that emphasis. The sources also point out that the AER is often even more useful because it includes charges beyond just a pure interest.
That inclusion is a consumer safeguard, and it's often mandated by regulatory bodies in many countries. The definition of AER is the total accumulated interest plus certain charges, like taxes and fees, that would be payable or earned up to the end of one full year.
Divided by the original principal.
Right. This gives you the clearest possible picture of the real annual cost or gain. If a bank uses daily compounding to make their nominal rate look attractive, the AER will pull back that curtain and show the effective rate after those 365 compounding events.
It is so easy to fall into the trap of thinking compound interest is a modern financial invention, maybe something cooked up in the 20th century.
Right, like it's a product of Wall Street or something.
Exactly.
Yeah.
But the sources we reviewed reveal its pedigree is incredibly long, stretching way back into antiquity. Okay, let's unpack this history. Where do the roots of compounding truly lie?
The practice is definitely not new. It was known to ancient civilizations, and we have remarkable physical evidence. The sources cite a clay tablet recovered from Babylon.
A clay tablet.
A clay tablet, yeah. It dates back to the period between 2000 and 1700 BC.
Wow. Over 4,000 years ago. What does this tablet show?
It appears to contain a problem involving the calculation of compound interest. While the context is, economic, the mathematical understanding of how a sum grows exponentially over time was clearly present in the Mesopotamian era.
So financial planning for long-term growth or debt management has been around as long as recorded history.
It seems so. It's a powerful perspective.
And yet, for much of the subsequent history, particularly leading up to the medieval period, compound interest wasn't just a standard financial tool, it was something severely frowned upon.
Oh, absolutely. Morally condemned, especially by Roman law.
Why? What was the controversy?
Well, in ancient and medieval societies, charging any interest was often viewed as usury and condemned by religious and moral authorities. But charging interest on interest compound interest was regarded as the worst kind of usury.
The worst kind.
They even had a special name for it: anaticism.
Why the special condemnation for compounding? What made it so much worse?
It was seen as unnatural. I mean, simple interest was sometimes tolerated as, compensation for the risk of lending your principal. But earning interest was viewed as profiting from time itself.
Or generating money from nothing.
Generating money from nothing, which was considered deeply exploitative. Roman law and the common law that followed in many countries severely restricted or outlawed the practice for centuries because of this moral judgment.
That context is so important, showing that finance is always intertwined with morality. Yet commerce and the necessity of long-term trade eventually forced a mathematical reckoning, right?
It had to.
So when do we see the first real written analysis of how to calculate this forbidden growth?
That begins to pop up in the medieval era. We see early written analysis surface through the records of practicing merchants. A key figure here is Francesco Balducci Pigalotti.
A Florentine merchant.
Right. His 1340 book, Pratica della Mercatura, contains some of the earliest detailed calculations.
And what kind of calculations are we talking about?
He provided a practical ready reckoner table. It detailed the compound interest accrued on 100 lire for various common mercantile rates, specifically from 1% up to 8%, calculated for periods up to 20 years.
So this wasn't abstract math. This was an essential tool for merchants to quickly estimate the value of long-term investments or obligations.
Despite the legal restrictions, yes, it was a business tool.
And shortly after that, we get one of the most famous rules in all of finance, one that speaks directly to the power of compounding and time, and one that every investor still relies on today.
The Rule of 72.
The Rule of 72.
That rule was presented in Luca Pacioli's foundational work, the Summa de Arithmetica, which was published in 1494. The Rule of 72 is perhaps the most elegant mathematical approximation in finance.
Tell us how it works and why 72.
It's designed for rapid mental computation. The rule states that the approximate number of years required for an investment at compound interest to double its value is found by simply dividing the annual interest rate as a whole number into 72.
So let's use a couple of scenarios. If I achieve a modest 4% return annually, how long until my money doubles?
You divide 72 by 4, which gives you 18 years.
And if I'm a riskier investor and manage to achieve a 9% return?
72 divided by 9 is 8 years. It links time, rate, and growth very elegantly, and importantly, it gets the job done quickly.
It's a fantastic mental shortcut.
It is. And while 72 is the most common number, the sources note that mathematically, 69.3 is closer to the theoretical ideal, especially for continuous compounding.
But 72 is easier to divide.
Exactly. 72 has more convenient factors. It divides cleanly by 2, 3, 4, 6, 8, 9, 12, etc., making it superior for quick mental estimation.
The rule of 72 essentially gives us a quick way to conceptualize that exponential curve. It shows us how sensitive the doubling time is to the rate.
It does. But the move towards truly modern, accurate calculation came in the 17th century. And here we have to highlight Richard Witt's Arithmetical Questions, published in 1613.
Why was Witt's work considered such a landmark change?
Because prior writers, like Pacioli, only treated compound interest briefly within broader mathematical treatises. Witt's work was wholly and exclusively devoted to the subject.
The whole book was just on this.
The entire thing. He was a London mathematical practitioner, and his book provided immense clarity, accuracy, and depth of insight. He wasn't just giving tables, he was providing the methodology.
And the detail was extreme for the time.
It really was. He provided 124 worked examples and included detailed tables based on the 10% maximum allowable interest rate in London at that time. This transformed compounding from an approximation or a side note into a fully formalized, rigorous field of mathematics.
Okay, here's where it gets really interesting, connecting this very practical financial problem to pure foundational mathematics.
This is one of the biggest aha moments in the history of mathematics and finance.
It wasn't just practitioners and merchants pushing the boundaries. It was pure mathematicians looking at the limits of compounding.
And the pursuit of compound interest led directly to a monumental discovery, the mathematical constant E.
The number E.
Yes. Jacob Bernoulli discovered this constant in 1683 while exploring a question about compound interest.
Specifically, he was asking, what happens when you let the compounding frequency or variable increase toward infinity?
Exactly. He asked, if I offer a 100% annual rate and compound it more and more frequently, monthly, daily, hourly, continuously, what is the maximum possible accumulated value?
And it doesn't just go to infinity.
It doesn't. He found that instead of growing infinitely large, the total value approached a finite limit, which we now know as E, approximately 2.71828.
That connection from Jacob Bernoulli studying a specific financial problem, the maximum possible return on an investment, to discovering the constant that governs all exponential growth across physics, biology, and engineering. That's just phenomenal.
It is. The engine of wealth is literally governed by a constant of nature.
It perfectly illustrates how practical financial problems often drive these theoretical breakthroughs that reshape our understanding of the universe.
And that practice of trying to tame the math continued centuries later. The sources note that in the 19th century, Persian merchants employed a simplified mathematical technique.
They used a modified linear Taylor approximation to calculate monthly payments. A Taylor approximation sounds like advanced university calculus. Why would a merchant be using that?
Well, they weren't using the full, complex calculus. They used a slightly modified, simplified linear version derived from the Taylor series expansion. The point was to create a method that allowed for easy, accurate mental computation of complex loan terms.
So without needing pen, paper, or complex tables.
Exactly. It shows this long human tradition spanning from Babylon to 19th century Persia of trying to tame the exponential nature of compounding for everyday commerce.
We've established the core variables and traced the concept through 4,000 years of history. Now let's see how that compounding frequency is manifest across modern financial tools.
Let's start with large standardized instruments like corporate and government bonds.
Okay.
These large instruments operate on a very explicit, standardized schedule globally. The standard approach is that the interest payments, often called coupon payments, are typically payable twice yearly.
Semi-annually. So the compounding frequency, N, is fixed at 2.
Yes. The calculation is straightforward. The interest paid every 6 months is the disclosed nominal rate divided by 2, multiplied by the principal amount.
But the key takeaway for the investor is understanding the effective rate, right?
Absolutely. Because you receive that first coupon payment halfway through the year, and if you immediately reinvest it, it starts earning interest for the remaining 6 months.
So the yearly compounded rate, the AER, is always slightly higher than the nominal rate stated on the bond, assuming you're reinvesting those coupons.
That's a subtle but absolutely critical point for you, the learner. If you are comparing two bonds, always calculate the effective annual rate based on that semi-annual compounding to get the true yield. Never mistake the headline rate for the actual rate of return if you are actively reinvesting.
Now let's move to consumer finance, specifically mortgages, which provide a fascinating contrast depending on where you live. Our sources draw a sharp distinction between Canadian and U.S. mortgages.
This is a perfect illustration of how legislation dictates financial structure. In Canada, mortgage loans are generally mandated by law to be compounded semi-annually.
So N equals 2 by law.
By law. It's a fixed, regulated feature of the loan structure, even though the borrower is typically making monthly or even bi-weekly payments.
So the Canadian lender figures out the total interest owed for that half-year period and then breaks that down into the monthly payment schedule.
Precisely. The interest accrues semi-annually, even though payments are more frequent. Now contrast that with U.S. mortgages. These use an amortizing loan structure, which handles interest in a fundamentally different way.
What does amortizing mean in this context?
It means the entire process is governed by an amortization schedule. Think of Canadian compounding like a semi-annual accounting day, where all the interest for that period gets calculated.
Got it.
U.S. amortization means you clear that interest debt every single month. Interest is calculated monthly on the remaining principal balance, but critically, that interest generated is paid off immediately by the monthly payment.
So the interest never gets added back to the principal to compound further because I'm paying it down every month. The principal only reduces with whatever is left of my payment after the interest for that month has been covered.
That's the key difference.
Right.
The monthly calculation happens, but the compounding effect on the principal is mitigated by the rapid forced payment of the accrued interest. It keeps the exponential curve of the debt from accelerating.
That's a great way to summarize the difference. Now let's move to the mathematical extreme we touched on earlier, continuous compounding.
This is where we revisit Jacob Bernoulli and the constant E. Continuous compounding is the mathematical limit achieved when the number of compounding periods per year, our n, increases without limit approaching infinity.
So interest is being calculated and added back to the principal every microsecond, constantly.
That's the idea.
Why do we care about this theoretical limit? I mean, it seems irrelevant to a homeowner or a typical saver.
While it is irrelevant for a savings account, it is absolutely essential for the dynamic pricing of complex instruments, especially financial derivatives like options and futures.
Okay, so why is continuous time preferred in those advanced markets?
It's a natural consequence of the type of mathematics required to model assets whose prices change constantly. When you get into higher level mathematical finance, specifically something called ETO calculus, modeling these rapid continuous price movements is mathematically simpler if you assume continuous time rather than discrete jumps.
Ah, so rather than trying to model quarterly or daily compounding.
Right. If the asset price is changing every millisecond, it's easier to model the growth rate as continuous.
I see.
Continuous compounding simplifies the math needed to value risk and expected returns. The constant E allows the models to assume a continuous stream of small changes. And as we mentioned, mathematically, we know the absolute ceiling for this growth.
The upper limit.
The effective annual rate under continuous compounding approaches the upper limit defined by E to the power of R minus 1. No matter how fast you compound, you can never exceed that rate.
We've seen how merchants tamed this math using approximations. Now let's transition into the quantitative core of our sources, the actual exact formulas that underpin those ancient tricks and govern modern finance. We're going to try and demystify these.
This is where we define the power of exponential growth explicitly. We begin with the periodic compounding formula, often called the growth engine formula. This is the general equation that calculates the total accumulated value A.
Give us the formula and then we'll break down every piece by what it does for us.
The total accumulated value A, which is the final amount, is defined by A equals P times, in parentheses, 1 plus R over N, all raised to the power of T times N.
Okay, that looks a little intimidating, but let's go piece by piece. P is easy. The initial money invested, the principal.
Correct. R is the nominal annual interest rate, always expressed as a decimal, so 5% is 0.05.
All right.
N is our friend, the compounding frequency, how often per year. And a key is the overall length of time, usually measured in years.
So that inner part, the 1 plus Rn, is effectively the growth rate per compounding period.
That's it.
So if I invest for 30 years at 8% compounded quarterly, so NZ of 4, I'm dividing that 8% annual rate into 4 periods. So every 3 months, my money grows by 1 plus 0.08 over 4, or 1.02.
Exactly. You are multiplying your investment by a factor of 1.02 every single quarter. And the exponent, Tn, is the total number of compounding periods over the entire life of the investment.
So in that 30-year quarterly example, the exponent is 30 times 4, 120.
120.
That massive exponent is the key lever, isn't it? That is the exponential power in action. That is why time matters more than the rate over the long run.
It is the exponential multiplier. And remember, the total interest generated, I, is simply the final amount, A, minus the initial principal, P.
Now, you mentioned earlier that mathematicians often simplify this by dropping the principal P. Why do they do that, and what is the resulting formula called?
We call that the accumulation function, $8T. Why drop P? Because the principal is just a scaling factor. Dropping it allows mathematicians to create a standardized model showing exactly what $1 grows to after time t.
So it lets you compare growth rates universally, regardless whether you started with $1 or $1 million.
Exactly. The accumulation function is simply that same formula without the PA of t equals 1 plus r over n, all to the power of tn. It tells you the factor by which any money will grow.
That makes perfect sense. Let's now revisit the highest boundary condition, continuous compounding, where n approaches infinity.
Right, which we established is critical for options pricing. Continuous compounding shifts the formula completely away from discrete countable periods and into the realm of the natural logarithm base e.
And the formula for the amount after time t with continuous compounding becomes strikingly simple, doesn't it?
Yes, the complexity of the discrete formula melts away, and we are left with P of t equals P naught times e to the power of ort.
So P naught is your initial principal, R is the annual rate, and T is the time in years.
And that simplicity is why it is preferred for modeling things that change dynamically and continuously. When time never stops compounding, growth is governed by nature's constant.
This leads us to a concept that is mathematically most abstract but conceptually vital: the force of interest, represented by the Greek letter delta.
The force of interest, or delta, is what we call the continuous rate when n tends to infinity. For the learner, don't get intimidated by the calculus notation. Think of delta as the instantaneous rate of growth.
The purest, most unadulterated measure of how fast your money is compounding at any single moment.
It's like a speed limit sign on the highway of finance, exactly. It's not an average rate over a year. It's describing the rate of change at every single instant in time.
So what's the relationship between this delta and our standard compound rate?
When the annual rate r is constant, delta is also constant, and delta is simply the natural log of 1 plus r. So delta ln 1 plus r. This tells you the specific continuous rate required to mathematically match the discrete annual rate.
That's critical. It gives us a way to translate discrete, real-world compounding into the continuous theoretical world.
And the comparative context is illuminating. The force of interest is always less than the annual effective interest rate, the AER, because the AER includes the total effect of the discrete compounding jumps, while delta sort of smooths it out.
Right.
And the sources bring this highly theoretical concept back to real-world economics, showing it's used not just for derivative pricing, but for modeling inflation.
Using something called Studley's formula.
Yes, which uses a time-varying force of interest to model inflation. The full formula is quite complex, but it shows the practical utility of these continuous growth models. They give actuaries and economists the tools to project long-term economic forces accurately.
Okay, that is heavy math, but the context is critical. Before we move on, we need to address the necessity of the modern financial market, converting interest rates between compounding bases.
This is a practical, everyday necessity for financial professionals. If you have an interest rate quoted at 6% compounded quarterly, so n equals 4, and you want to compare it to an equivalent rate that compounds monthly, where n equals 12.
You have to convert one to the other.
You have to, otherwise you're comparing apples and oranges. You need to ensure they yield the exact same total accumulated value over a year.
So what's the conversion formula for that?
The general conversion formula is a bit of a mouthful, but what it's doing is simply forcing the growth factor of the first rate to be equal to the growth factor of the second, ensuring they are truly equivalent.
And if we want to convert a discrete rate, say our monthly compounding rate, directly to the continuous basis, the force of interest.
We use a formula derived directly from the definition of delta. Delta equals NN1 plus RNLA. This allows any discrete rate to be seamlessly expressed in terms of its continuously compounded equivalent.
We have established the engine and demystified the formulas. Now let's apply this power to the financial tools that affect almost everyone. Amortized loans like mortgages and long-term savings plans.
We'll start with monthly amortized loan payments. We established that calculating the smooth monthly payment is a fundamental application of compounding mathematics.
This is the smooth payment calculator. It's the formula that spits out that magic number, what you owe every month for the life of the loan.
It is a critical piece of financial engineering. The exact formula used to calculate the smooth, constant monthly payment, which we'll call C, is C equals R times P divided by, in parentheses, 1 minus the reciprocal of 1 plus R to the power of N.
Let's clarify the variables here, as they're a bit different. P is still the principal, the amount borrowed. What are R and N in this specific context?
Crucially, R is the monthly interest rate. You must take the nominal annual rate and divide it by 12. So a 6% annual rate means R equals 0.005.
And
And N is the total number of payment periods, not the frequency, but the total count. For a typical 30-year monthly loan, N is 360.
the denominator looks very much like a present value calculation. It's ensuring that if you took every single one of those 360 payments, discounted them back to today, they would perfectly equal the original principal P.
That is precisely what the formula is doing. It is relating the present value of an annuity, that fixed stream of future payments, to the lump sum borrowed today.
Now that formula provides the exact smooth payment, but let's go back to the ingenuity we discussed earlier, the power of approximation. The sources detailed a high-accuracy, simplified formula used historically.
This is a fantastic example of mathematics meeting necessity. For typical interest rates, where the monthly rate R is tiny compared to 1, we can use a simplification based on Taylor approximation.
Where the natural log of 1 plus R is approximately equal to R.
That's the mathematical trick, and it's what allowed those 19th century Persian merchants to do this in their heads. The source suggests defining 2 auxiliary variables to make this approximation cleaner. First, you define a term called C naught, which is P divided by N.
So what is that?
This is the theoretical monthly payment if the loan had 0 interest. It is just the principal divided equally over the payment periods.
That gives us a baseline payment we can easily calculate in our heads. Okay, so let's walk through the specific concrete example provided in the sources to show just how accurate this historical method is.
The example is a substantial common scenario.
Right.
A $120,000 mortgage with a term of 30 years and a nominal rate of 4.5% payable monthly.
So 30 years means N is 360 periods, and R is the monthly rate, so 0.045 divided by 12, which is 0.00375.
First, that 0 interest payment, C naught, that's simple division. $120,000 divided by 360, which is $333.33.
Okay, that's our baseline.
Right. Then we use a simplified approximation formula provided in the LARS. You calculate a factor, let's call it x, which is 1/2 times n times r. For this loan, x comes out to 0.675.
And the formula.
The practical folk method is that the payment, c, is approximately c naught times the quantity, 1 plus x plus 1/3 of x squared.
So we plug in those numbers. C naught is 333.33 and x is 0.675.
And when you run that calculation, the approximate payment comes out to be about $608.96.
And the actual exact payment calculated using the complex formula we saw earlier.
The exact payment amount is $608.02.
Wow. 608.96 versus 608.02. That approximation is off by less than $1.
About 94 cents, an error of about 1/6%.
That shows the immense practical power of simplifying calculus for mental computation, especially in an era without ubiquitous computers.
It speaks volumes about the human need to tame complex financial math for everyday transactions.
Now, let's pivot from debt back to growth savings and investment plans where you have an initial lump sum P and you make regular recurring deposits M.
This is what most people are doing with a retirement account.
Right. So in this scenario, we have two components growing simultaneously. The original principal grows via the standard compounding formula.
And the stream of monthly deposits are essentially a series of small deferred principals. Each one of those contributions is a new investment that starts compounding for a shorter duration than the original lump sum.
So the calculation has to sum up the future value of the original money plus the future value of every single subsequent monthly deposit.
Precisely. The formula relies on recognizing that the sequence of recurring deposits forms a geometric series. We sum up the future value of every single monthly deposit made over the total time t.
And the total accumulated value, which we'll call P prime, combines both the compounding series and the initial principal.
It does. Assuming r is the monthly rate and t is the time in months, the formula has two parts. The first part is m times the quantity, 1 plus r, to the t minus 1, all divided by r. That's the sum of the deposits.
And the second part?
The second part is just our familiar growth engine formula for the initial lump sum, so p times 1 plus r to the power of t. You add them together.
The ability to use this closed-form solution simplifies what would otherwise be 360 separate calculations if we were doing a 30-year monthly calculation manually.
It gives us an immediate, exact answer for the future value of a constantly funded savings plan.
And that wraps up our deep dive into the engine of wealth and debt. We started with a simple definition, immediately established that critical difference between simple and compound interest.
And then we jumped into the real mechanics compounding frequency, N, and the standardized yardstick, the annual equivalent rate, or AER,
which we established is the only number you should trust when comparing financial products.
We covered 4 millennia of history, tracing the concept from ancient Babylonian clay tablets through the condemnation of compounding as usury in Roman law, all the way to Pacioli's elegant Rule of 72.
And crucially, we saw that Jacob Bernoulli's study of compound interest in 1683 led directly to the discovery of the fundamental constant E, the bedrock of exponential growth.
We analyzed the financial landscape, comparing the regulated semi-annual compounding of corporate bonds and Canadian mortgages with the actively amortizing monthly interest structure of U.S. loans.
And we dove into the complex mathematics, demystifying the periodic compounding formula, the role of E in continuous compounding, and the highly technical concept of the force of interest used for valuing derivatives and modeling inflation.
Finally, we applied those principles to practical formulas, the exact calculation for smooth monthly payments on loans, and the highly accurate historical approximations that prove the ingenuity of finance.
The scope of compound interest is truly enormous. It dictates the timeline for retirement, the total cost of a home, and the profitability of global financial instruments. It is the concept that separates just saving money from truly investing.
And we noted that continuous compounding is not just theoretical, it's crucial for pricing advanced, rapidly moving financial instruments. The force of interest is a measure of this continuous growth, and we can model highly complex economic phenomena like inflation using it.
This raises an important question for you, the learner, to consider as you manage your own portfolio. If mathematically continuous is the theoretical limit of compounding, if money is growing every microsecond, what does the real-world utility of continuous compounding tell us about the ideal frequency of reviewing or rebalancing your own long-term investment strategy?
If growth is constant, how close should your financial attention come to that continuous time limit? Is a quarterly check-in sufficient? Or does the continuous nature of modern markets demand closer, more frequent attention?
Something to mull over until our next deep dive. We hope this has equipped you with the knowledge to not just participate in the financial world, but to truly understand the mechanics, the history, and the powerful math that underlies it all.
Till next time.